have the same information. All right, so yeah, hello everybody. And so today originally I was planning to do a little bit more advanced stuff. Advanced stuff, day was too long. So regarding regression, but so basically based on the questions that I got from you, I realized maybe it would make sense to go over the regression diagnostics and like the individual steps in more detail, and to reiterate what all these things mean and how to look at the plots. And so because it's a lot, right, so that you have to pay attention to when running a regression analysis. And so I thought maybe we're taking the time today to go like one more time over all that stuff. And then so next week we will talk about the more advanced topics, and then of course also do multiple regression in R. So that's the plan for today. And also I wanted to give you like a little bit time at the end. So as we had discussed last week, right? So at least 20 minutes so that you can discuss with your group members either any open questions from the current assignments, as the one that is due tomorrow night, or the assignment that is due next week, which will be multiple regression. And so again, we will talk about the, oh, okay. No, it's not due next week, right? It's so so that wouldn't work because we are not talking about multiple regression today. So let me check that. So whether the timelines are still aligned with our tutorial. So otherwise I will extend the deadline by 1 week because we haven't talked about multiple regression yet. So one more thing, so if you post your feedback on our suggestion box, I appreciate it, and also you're getting great credit, right? So please post your name, otherwise otherwise I do not know who you are. So whoever posted something without including their name, so please let me know it was you, otherwise I cannot give you credit. I mean, if it was like a supposed to be an anonymous post, then it's fine, but otherwise please let me know. And also it is due Friday, right? So Friday, not Monday, Friday. Okay, so moving forward, I'll take those things into account. So later tonight I will also, as I had announced last week, I will also post more, so our next paper for our discussion, and then I will post the questions for the basically makeup assignments that you can use for grade improvement. So the first one, and then will probably be on one of the for one of the articles that I had already posted before. All right, so okay, so let me just open. Yeah, sorry about that. So my last minute email, I hope you have all seen it. So we are basically using the same data sets that that you should be familiar with already. And so we are also using toolboxes that we have used, libraries that we have used before, packages that we have used before. So hopefully, so nothing will be a big deal. So you shouldn't have any installation problems. At least not significant. Alrighty, so let me just quickly open. So where are they? 1 second. So I created on R a markup file for regression analysis that is only for simple linear regression, and also for bootstrapping simple linear regression, which we hopefully will be able to talk about towards the end of today's meeting. Let me just share my entire screen. All right. So, fantastic shopping occupancy. Are you all, sir? Are you all able to see the file on my screen? Yeah. Okay.
Yes.
Yeah. All right. So as I had mentioned before, so we are going to work again with the albums album sale one data set. So that's on Blackboard and that you should all have in your workspace already. And so just a reminder, right, so it contains 200 cases, so it means 200 rows of data. So each of these cases represents a different album. And so it has only two variables. So one is called AdWords. That's the amount of money that was spent advertising the album before it was released. And then it has a second variable, and that is sales. And that is the number of albums sold in the first week after its release. And so it's all in thousands of whatever unit, yeah, dollars, pounds. So it's from a British textbook. So, so in that example, those pounds, but doesn't really matter, right? So that means the AdWords variable is the predictor here for our example, and then the sales variable is the outcome. And so we are estimating a simple linear regression model that predicts the number of sales from the amount of money that has been spent on advertising the album, right? And these are the two columns in our data set. And so, of course, so first we are reading in the data as usual, so that you should all be familiar with that. So hopefully no problem anymore. And then, so what I just explained, right? We have the 200 rows. So in this case, each row is one album, right? So it's in this case, no participants or whatever. So the units here are albums. And then we have the two columns that are our two variables. So for one, the predictor variable, advertisement, and then the outcome variable, sales. All right. So, and then, so you probably all know by now that we are using so the function lm in R to fit our linear model. And so what R does in the background, I mean, it does many things, but so the most important thing is that it basically estimates the coefficients for this regression model. And so that means because it's a simple linear regression model, it means we have only one predictor, we have one coefficient for slope and one for the intercept, right? So then, of course, it gives us all sorts of other useful information so that we need to make inferences to generalize our findings to the population. And so that is our F statistic to tell whether the R squared, so the amount of variance, is a proportion of variance that so our model explains in our outcome variables, so that means in the sales numbers, what that number is, and whether, so of course we get the R squared itself, and we also get the F statistics that tells us whether it's significantly better than a null model, so that basically only has an intercept but no predictor, so a model that predicts the mean of so the sales numbers for each value of the predictors, for each basically irrespective of how much money was spent on advertising. And so then again, as a reminder, that's very important, right? So when we are fitting this model, so our coefficients are coefficients that we estimate from our sample, right? So the model is for our sample. And what we want to do is so also our R squared, right? So how much, so what the explained variance is for our data. So what we typically want to do is we do not only want to describe our sample, right? So we want to generalize to the population. So we do not only want to know what's the case for these 200 albums, we want to know what is the general relationship between so the money that we spend on advertising and how that affects the sales numbers, right? So for any potential future releases, right? That is something that so companies might be interested in. So not only for this example. And so that means what we are estimating is the true population parameters. So we want to know what is a true regression model in the population. And what we are basically using is our best guess, our best estimate are our parameters that we have calculated for our sample. And in order to be able to make that inference, right, so this generalization to the population, so certain assumptions have to be met. I just wanted to remind you right now, right, so that there's always a difference between what we are fitting for our sample and whether we can generalize it to the population or not. So that we always, right, that we always keep that in mind. So what we are estimating is a model for sample. We see that as an estimate for the underlying population model, but of course that is always unknown, right? So our true regression function is unknown, so that is not knowable. We just make a best guess. All right. So, and then I guess you're all familiar, right, with the formula. So are there any issues with the regression formula, or is it pretty clear how to input the, is it clear how to run the regression model with the LM function? Yeah, okay. So, all right. Please let me know if there are any open questions. Okay. So, and then I mentioned that last week, right? We went over that. So when you're calling the LM function, so it will create so this object, so the regression object in R, which is nothing but a list, and the list has different elements. And not all of them are important. So for us, so the most important are the coefficients, the residuals, right? So then the fitted values are important. So the degrees of freedom, et cetera, et cetera, et cetera. So the model, of course. And so that is just so that usually we don't look at it's a raw model, right? So we're instead using the lm.summary function, which gives us a nice like summary of the information that's important to us. But I'm just including that to encourage you to always look behind the curtains and see what R is actually creating, right? So the more advanced you get, so the more you will actually work with what's there, and you want to access those objects and you want to manipulate them. So, right, so always basically be curious, look into what's actually generated and how it looks like. It's often very helpful, right? So, but yeah, don't sweat it. That is just for your information and to encourage you to look a little bit behind. So what's going on, and so right, and as for any other, so a list object is actually similar to data frame. So it's more flexible in the sense that it can contain elements that have different types, right? It can be numbers, strings, vectors, can be another list inside. So the elements, so it basically it's a container for different types of objects, right? Whereas for data frame, it always has to be the same type. And here in a list, you can put really different elements. So you can make some crazy collection, right? So, but you can access the individual elements in a list also with the dollar operator, very much same way as you access the columns of your data frame. So, all right. So what we, in most cases, right, if you fit your regression model, so what you're, as I said, what you're using is a summary LM function, right, and that is the model that we fitted, right, so you call that as the, call this function with your fitted regression model as the argument. And so you get all these, right, we talked about last week, so these pieces of information, so like the minimum, maximum, the first quartile, the third quarter, and the median for residuals, that would be relatively symmetric. Then your coefficients, right? So in this case, the intercept and your slope, right? So the regression coefficient for your predictor. And so, and then I basically included so the information that was also in the other tutorial already. So I modified a little bit or added a little bit. So, and please make sure so that you really understand what it means. So the estimate is, I mean, it's pretty straightforward, right? So the estimate is just the point estimate for your coefficient, right? So that's what basically what you put in to specify your model. And so that what basically it's your estimate for the mean, right, of your so for the predictor, it's the it's basically an estimate for the mean of your, so how you fit the mean of your conditional distributions, right? So always keep that in mind, right? So that you have, like for each predictor value, you have a distribution of your outcome values, right? And so what we are trying to predict is the mean of this distribution. Right? So for each x value, for each predictor value, we're trying to predict the mean of the distribution of the corresponding y values of the anyway. So, so first of all, we have our point estimate of the coefficient itself, right? And then the next value here is our standard error, right? So that means, so don't forget, it's so we, right? So we when we are talking about statistics and then about generalization, right? So it's always this idea of the sampling distribution that is behind our statistical tests. So that means if we would basically from the same population, right, of albums released now in the world, yeah, all albums, so that are that can be released. So if we would basically draw independent samples of the same size, and we would do that over and over and over and over again, right? So for each of these samples, so we would fit the regression model. Then, so we would get like different values, right? So different estimates for our intercept and for our slope. And so this distribution has a standard deviation, and this standard deviation is a standard error, right? So for our coefficient. And then we divide our so and then of course, so what the standard error here means, that is under the, basically that is a standard deviation of our sampling distribution under the assumption of the null hypothesis. So what does it mean? So the null hypothesis basically assumes that the true value of the coefficient is 0. Right? So which, and for the intercept, I already told you that doesn't mean anything. It basically just it's a scaling thing. So basically just tells you whether a mean of your predictor and your outcome variable are different. So, but for so what you're really interested in is whether your slope parameter is 0 or non-zero. And if it's 0, right, so then you have no relationship between a predictor and outcome. So in your standard, your sampling distribution is this theoretical distribution under the assumption that your true slope / intercept, right, we just don't care that much about the intercept, that the true coefficient is 0. Yeah, so how would that look like if we had a population where there was actually no relationship between the amount of money that we spend on advertising and so the sales numbers? If we had such a population, so what would the distribution of the slope estimates look like if we would do that theoretically an infinite number of times, right? So draw the sample of 200 albums. And then, of course, the mean of the sampling distribution is expected to be 0, right? The true population mean, the true population parameter. And so, and then we, of course, for the individual samples that we are drawing, so this value would vary, right? Of course, this true mean, and that is our standard error. Yeah? Always the same idea. And then we get the t-value by dividing our estimate by the standard error, right? So we don't need to, basically in theory, we would have to subtract the mean, but because the mean of sampling distribution is 0, right? Because that's our assumed true parameter. So we are just dividing our estimate by the standard error. They can do that by hand. And you'll see you get the t-value here of 17.799 for your intercept and 9.979 for the slope. And then you can determine the p-value that corresponds to this t-value. Right? So t-value, again, is distribution, you know, it's similar to the normal distribution, just better tails. Depends on so the sample size, how much it deviates from the normal distribution. The larger sample size, it's getting more similar. Here we have a pretty large sample, so that basically more or less that looks like a normal distribution. So, and then so the p-value basically answers the question, so how likely, so what is the probability to get a coefficient, so that is, or like a deviation, right? So that is as large as we see in this sample, right? So what is a probability to get an advertisement, so the slope coefficient for advertisement that is 0.1 if the data came from a population where the true slope is 0. And so this probability is very, very low. Yeah, it's very low. It's actually almost 0. So in this case, if we get a result like that, so we are of course tempted to think, well, maybe they are not unrelated. But then keep in mind, this is a frequency-based account. So a single outcome doesn't tell us anything, no matter how small the p-value is, right? So that is always in the long run. Yeah, so if you would be the first researcher that investigates this question, and you would be the first one to get that result, and it might indicate that this is worth further investigation, but doesn't prove anything, right? So you haven't shown or proved anything. You have found something that is interesting and worthwhile of further investigation, but it doesn't mean that that you have, right? So because you've got this fantastic small p-value, that does not mean that you have proven that proof it's, yeah, never mind, you know what I mean. It's no proof that there's actually a relationship between the two variables. Yeah, so these are just a few reminder of these basic concepts, right? And always keep that in mind. So what your statistics actually mean, what the standard error means. A standard error always refers to this idea of sampling distribution, standard deviation of sampling distribution, right? And that you basically test how probable is that under the assumption of my null hypothesis. So keep in mind what your null hypothesis is. Right? In this case, your null hypothesis is the true slope is 0. You know, true intercept is 0. Don't care what's intercept. All right. So, and then you have your, so the next, this is clear, right, what the codes are. And then you have a residual standard error. And so also tells you what the degrees of freedom are, right? So the residual standard error is so roughly 66. So sorry, yeah, there was some mix up in my previous tutorial where I had basically used numbers from different, suddenly I started using a different data sample, my apologies. So I've corrected that here. So the underlying idea was the same, but was not quite consistent. So, okay, so what is the residual standard error? So, I mean, you know what basically the mean residual, so the mean sum of squares for residuals is, right? So the mean deviation of your, basically of your, as a mean squared deviations of your observed values, so the observed outcome values, in this case, your observed sales numbers from your estimated regression line, right? So that is something that you can directly calculate from your model. Yeah, you just have to basically sum over all observations in your sample. You just have to determine how much does this individual observation, this data point, deviate from the predicted sales number based on the regression model. And then you calculate the square and you sum it up across all observations, right? And so then you're dividing by the degrees of freedom for the residuals, which are number of cases minus 2. And then you get your your mean squared residuals for this model. However, so what we are actually interested in is, so what is actually the so the deviation or the variability of the residuals, so basically the, right, so, or conditional distributions from the true regression line. Yeah, so not from the one that we estimated from our sample, but from the one that is true for the population. So if we basically would sample the entire population, right, and include all potential observation units, so and then estimates the regression model. So then we would get the true regression line, so the true function. So that means there are two elements of uncertainty, right? That is the the variability of or the deviation of the observed y-score, so here the observed sales numbers from the estimated regression line, and then also the basically the variability of this estimated regression line, so from the true regression line from sample to sample. And so the larger our sample, so the smaller is the variability, basically this variability that is caused by the error that we are making in the sampling error that we're making estimating the regression line. And the more important is actually the variability of our outcome data, so the sales numbers, so around the spread around the regression line. So, and our, long story, but our residual standard error, right, it's an estimate of the, right, so the variability around the true regression line. Yeah, so that is not something that is different from, and we're estimating it based on our residual variance that we see in the sample, but that is an estimate. It is not the same thing, right? So keep that in mind. And here, so our estimate is that, so on average, so we see like a deviation of 66, right? Thousands albums, so that, and then it's albums sold, right? In units of thousands, so 66,000 is the mean deviation, right? And then again, keep in mind that is a squared number, so it doesn't necessarily make sense to interpret that. All right. And then also a reminder, right, so we have our multiple R squared. So in this case, it's not really multiple because we have only one predictor, so it's a simple regression model. So, and in our sample, so the model explains 33% of the variability of the outcome variable. That's pretty good. Although there's not really, I mean, it's really hard to say what is a good number for R squared and what is a bad number for R squared. It totally depends on your research question and your subject matter. In physics or some other science disciplines, that would be a horrible, in many cases, it would be a horrible R squared, right? You can get an R squared that's really close to 1. For the social sciences, it's a fantastic R squared. So it's really hard to tell, and you have to compare that to other studies that are in your field, right? And that are investigating a similar question. And then, so again, also just a repetition or a reminder, so the adjusted R squared is necessary, so that's basically an estimate of the true population R squared. So this is our sample R squared here. We have learned that it's positively biased, so it's always an overestimation for the simple reason that the R squared can never be smaller than 0, right? So we have this lower limit. So that means for if it came from a population that had a true R squared of 0, we basically cannot go lower than 0, right? So we would have basically, that is our limit or bottom. And so that means we would have like a few samples where it's actually larger. And then on average, so we would push our R squared in the positive range, right? So that's why we're overestimating so the true R squared. It's similar to what we have discussed about the correlation coefficient, right? So which also has these limits of -1, and that causes a bias. So in the adjusted R squared just controls for this bias, and so the bias is reverse. So the larger the number of our predictors, and the smaller our sample size, right? So, and the adjusted R squared accounts for that. So in here it's almost identical. That's good, right? And then we have our F statistic, which basically tests how much better, so how much more variance in our outcome variable is explained by our models and by our regression line as compared to the residual variance in our outcome variable. So right? So if we, and that is all relative to the mean of our outcome variable, so how much variable or deviations say are accounted for by the regression model. That means what is basically the squared so the sum of the squared deviations of the regression line from the mean of the sales, of the album sales in relation to what are the mean deviations of our actual sales numbers from those that are predicted by the regression line. And so the larger the, right, so these are the two components. So we basically break down the variability of the sales numbers in these two components, right? So the one component explained by the regression model, the other component not explained by the regression model, right? So residuals. And so the larger the explained portion relative to the unexplained portion, the better, right? And so more likely it is that so our data comes from a population where there's an actual R-squared and non-zero R-squared. So, okay, then let's move on to the regression diagnostics. So, and it's basically so always the same, right? For each simple linear regression model, so for the multiple regression, we talked about that there's like a couple of additional assumptions so that we have to take into account. So you have to check, and that's also when I'm asking you, like in an exam or an assignment, right? So when I'm asking you to check the assumptions, so please comment on all these assumptions, right? All of them. If you can tell because you did not conduct the study, so then just say so, right? Say, well, I cannot tell whether the errors are independent or not because I have no information about the design of the study, how the data was collected. I have no other information, so I cannot test this, right? So this is something that has to be ensured mostly by good design and so a clean implementation of the study, but right, post hoc, I cannot tell. So, but right, if I don't specify that I just want to hear certain things, always go over the entire range. Okay. So our outcome variable must be continuous, right? It's not a no-brainer. I mean, we went over that. I think it's pretty clear. So the predictor must have non-zero variance. So it's already relatively clear. Okay. So linearity, and that there I think was like a little bit confusion. So linearity means that's the expected value of our dependent variable. So that means basically our y hats. Yeah. So for each value of the predictor is a straight line function of our predictor variable. Yeah. So and that means that all conditional distributions of our outcome variable. So that means the distribution of our sales numbers that belong to a certain to a certain number, to a certain amount of money that we spend on advertising. So that all these, so the means of these distributions fall along a straight line. Yeah? So that is what the linearity assumption means. Also, you can think about it in an easier way, right? So it just means that you can describe so the relationship between these two variables using a straight line. But this is a little bit more formal definition, right? So that means that your conditional distributions, right? So think again about this graphs that we had in class on the slides, right? So that we have for each predictor value, so for each amount of money that you spend on advertising the album, you have, so right, so let's say you spend $1 million, so you have a number of albums that share that value. So, and then you have a distribution of their sales numbers, right? So they don't all have the same, so there will be some variance. And the idea is that the means of these conditional distributions are on a straight line. Okay. So then our assumption of homoscedasticity, and that basically means, again, so that is all, right? These are all these conditional distributions. That means that for each value of the predictor or the predictors, right? So for each combination of the predictors in multiple regression, so the variance of our residuals should be constant. Right? So that means it shouldn't, how much spread we have around the, so our regression line of the residuals, that should not depend on the value of our predictor. It would be constant, it would be the same for all values of our predictor, right? So residuals should spread around the regression line by the same amount. So the third assumption is also centered on these conditional distributions, right? Is the assumption that our residuals are normally distributed, right? So that basically equates to they have a mean of 0, they have the same standard deviation, so they have the same variability, and they are all normally distributed, right? So they're not skewed. They all have a normal distribution. And so, as I said earlier, we also, a very important, said it many times, so perhaps the most important assumption of regression, or linear regression, is that the error terms are independent. Unfortunately, it's hard to test, and especially not if it's not our study. So if we don't know how the data were collected, if you don't have any order-related information. So I mentioned that previously, right? If it's your own study, so what's always worthwhile is to check whether you see some trend in time. So just plot the residuals by, if you have like a study where you, right? So where's the data for each subject were like collected in a certain order. So it's always worthwhile plotting against, so the residuals against the order in which the data were collected, to see whether there are any sequential dependencies, or any order correlation in the data. But as I said, so without any further information, it's really hard to test. And then we also need to check for influential cases. Yeah? So for those outliers, and then again, this differentiation between outliers and in influential cases. So outliers are just unusual values, right? So there are so they could be univariate outliers, so it could be an extreme predictor value, extremely low or extremely high, right? So unexpected. So if you assume that the data follow normal distribution, either predictors or outcome variable. It could be bivariate outliers that are extreme X and Y, or have like huge residuals. But not all outliers are problematic for a regression model. It's just those outliers that have a substantial influence on the fit, so on the estimation of the coefficient. So outliers that pull the regression line towards them, right? So those are influential outliers, and those we need to worry about. The other outliers are not necessarily problematic. Okay, so how to check for these assumptions. And so it's always a good idea to look at the univariate distributions first. And you can, I mean, there are all sorts of options that you can choose. So you can use box plots, you can use histograms, right? So what I'm doing here is just histograms for our data sets. And then it's just a comment. If you're not sure how to determine the bin width, you can let R do that. And so what you're basically, so you say, okay, bin width is a function of my data. And I just give R the range, right? So I calculate the difference between the maximum, so my maximum data point, and my minimum data point. And then it's just something that R does internally. Here's its n class.ffd. So that's basically, so for this particular data set, so that determines the optimal number of categories or classes. And then you just divide this range by this number of categories to define how wide your bins are, right? So you can let R do that for you. And if you're unhappy with the result, you can still change it manually. So here I had R do it automatically because I used the facet rep option, and that can get a pain in the butt if you want to like have individual values for each of your each category, so for which you want to plot your data, so then it can get like difficult or difficult. Anyway, so and it's also always good to plot the density function on top, right? It's a little bit, just a little bit to add a little bit smoothing. It's basically, it's not really, it's not a theoretical density. It's basically just so it smoothed histogram, right? So and that compensates a little bit for a bin width that is not optimally chosen. So and it's always a good, it's good to double check, right? So, and what we see here for our example is that, the sales numbers look pretty good, right? So it's pretty symmetric, so no concerns here. Whereas the money that's spent on advertising shows a relatively clear positive skew, right? So we have, so most of the data are centered here in this area until maybe 1250, and then we have so a few more extreme cases. So there are a few albums where the companies spend considerably more money on advertising. So you have a few very extreme positive values here. And then you also see something that's a little bit unusual here, that so basically you have this high number of albums that have the lowest, basically a really low advertisement budget. So that's a little bit unusual and certainly not ideal, but that's problematic for our regression model. We're going to see, right? So it's just something that we are noting right here. It's always good to also plot the normal curve on top of the data. And then here, that's what I did for our example as well. So also note that in order to make these the facet, so basically these two plots in one figure, more or less. So it's just two facets of one output. So we have to transform the data into long format to do that, right? So from wide to long. And so that is nice. You can also do it individually, right? So you can do that over and over again. So you just pull out your variable and then you plot it for each. I'm lazy, right? I don't want to type it that often. So I just use the facet wrap option here, which basically allows you for the right, so the different subcategories of your get a qualitative, like a categorical variable, if you recode them into long format. So all your values are basically in one column, and then you have another column that tells you, is that sales or is that advertisement, right? So that is like a factor, sort of. And then you basically can plot by factor in these different panels here. So a disadvantage is if you do that it's a little bit harder to plot the the superimposed normal function. So don't get crazy about this code here if it's not, especially this part, if it's not 100% clear to you, no problem. Just go ahead and do your plots for each, so individually for each variable. Do your plot for advertisement, so pull out advertisement, do your plot for advertisement, pull out sales and do your plot for sales. So basically use two identical chunks of code, just right, so we put the right variable in there and do it that way. I just included it for those of you who are interested in how to do it, and also because I was so interested myself how to do it if something appears simple and then it turns out a bit more difficult. So, right, I just wanted to tell you, don't get upset if it's not 100% clear what the code is doing. That is just to save typing. All right, right? But so what that basically confirms what we've seen before. So we see this positive skew here for the advertisement, and so it's basically a symmetric distribution for sales data. Yeah, and then if we do box plots, then so that is confirmed. So this pattern, so we see for sales, right, looks all nice and symmetric, so we don't have any outliers. For advertisements, we clearly, again, we see this positive skew, right? So that's basically the so the distance between the The smallest value in the median is much, much smaller than the distance between the median and the largest value that's not considered an outlier. So, right, so that sees the system, so that basically, right, system, the whole distribution is leaning towards the left. And then we have these, so in addition to this long tail here, we have a few outliers. And so we see this, right, that is always also confirmed by our numbers here. If you look at the skewness, then we see we have, right, so we have a positive skew here, it's 0.8, so moderate to large positive skew in our data. And so the, or basically 2 times standard error is 2, so that is 2.44, that means the skew is 2.4 standard deviations above the skew that we would expect if the data were normally distributed. So I think that is outside our range, so our 95% range. So we are willing to accept the, so this idea of the possibility that the data might not be normally distributed, but might be skewed. And so then it's also, right, the Shapiro test is also significant here, right? So you see that the p-value is much, much smaller than 0.001 or 0.01, whatever you want to use as criterion. And then because I got this question here, I just wanted to reiterate it. So this is so R often plots in many programming languages. So plots things in scientific notation, right? So the numbers. And so this basically E means it tells you what you need to do with the output. So you basically multiply it with certain power. So with 10 to the power of something. And if this sign here in front of the, before the number is a negative one, then it's 10 to the power of minus, so negative 8 here. And if it's positive, then it means 10 to the power of 1, right? So basically, so let's just go over that here, right? So what does this here mean? So that basically means that it's 5.3. I save myself the remaining numbers here. It's 5.3 times 100. Yeah, it's 10 to the power of 2. So this is 6.1 times 100. 3.4 times 10. 6.7 times 10. And it's 2.3 times 10,000. Etc. 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 Yeah, and so if it's basically, also you can think about it that way. So this here, this number tells you if it has a plus in front of it, it tells you how many decimal points. So how many, what is it called? So it's a point. How many places you have to move it to the right, right? So if it would be a 1, then it would turn into a 67. If it's 2, it would turn into a 677. If it's 3, it would turn into a 6,000, etc., 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 right? If it's negative, you have to move the decimal point to the left. Yeah, so here it's minus. So that means instead of 7, it's 0.7. Yeah, so it's and negative power, that means 1 over 10, right? It's times 1 over 10 or divided by 10. So here is a case where it's 10 to the power of 0, so 1. Well, that means here we have a case where it's 2.44, right? So that is exactly the same. Here it's 10 to basically 1 over 10 to the power of 8. So that means you have to divide that by 100 million, because that's what 10 to the power of 8 is. Yeah, so that's what the scientific notation means. So, and it's important to get used to reading that, because so it's very common in programming languages that it's out, right? Because you cannot. It's first, it's really an eyesore to look at those numbers. Otherwise, right, you cannot count all these zeros when you get the full output, right? So that's why it makes much more sense to print it that way, because then you have also much more precision in your output, right? So you know exactly. So what you have basically you get much more information, right? So because otherwise, the computer can only print that many places. right? So if it would waste it for all the zeros, then it would actually lack the important information. So, okay, I hope that is clear, right? Just wanted to reiterate that. And so here this p-value is really small, right? It's almost 0. So if you see something like minus 0.08, minus 0.06, minus 0.04, so that's really, really, really small. Okay. So yeah, so we're basically our descriptive statistics here confirm what we've seen in our plots, right? So we have this skew and then non-normal, so as a consequence, non-normal distribution of sales of advertisement budget. Okay. So if you want to test the remaining assumptions, so it means linearity, homoscedasticity, and of course outliers. So it's always good to check so this a scatter plot and the residual plot. So especially for, I mean, the scatter plot in case of multiple regression doesn't make too much sense, although you can still plot the so one predictor against the outcome then for each individual predictor, but it's not. It makes most sense if you have bivariate relationships, so for correlation and simple linear regression. So you could, if you wanted to, right? I just sometimes I show you certain options and R. If you wanted to, you can create a scatter plot that is labeled by ID numbers. Yeah. So if you want to do that, so if you want to look at that, so you can do that using so. Oops, where's my command? Disappeared, don't know why, sorry about that. So here should be our, that disappeared. Ah, no, I'll correct that. Okay, for now I will correct it in what I'm uploading, so just suppress the output here. So I will include the code later and then upload the document again. All right, so but that is maybe not so nice to look at, right? It gives you like immediately so the number of cases that might be a little bit problematic. So we can also use ggplot, right? And then just using our point geome so that it's smooth, so that's our fitted line here. And so if we do that, then so we see nothing that is like super terribly concerning. So we just see, so basically it confirms this positive skew in our advertisement, right? We see that the majority of the data points clusters here in this lower area, right? So it's like in this lower half of the plot, and then we have relatively fewer data points that are in the upper range here. So we have like fewer albums that get a lot of money. Right, so that means we basically have, and then we see we have no data where a lot of money was spent, but so the sales numbers were low. So basically, if the companies put a lot of money on advertisements, so that also almost always paid off, apparently, right? So so the sales numbers are high. But then for the lower investment, we see a lot of variability, right? So we see high and low sales numbers, and so whenever we see a pattern like that, so you basically have to think about two options. The first one is that your model is not ideal, right? So that you could improve your model. And one possibility is that you may need to include additional predictors, right? So we could, for example, here, you could think of something like the popularity of the artists. So that might play a role, right? If an artist is super popular, so they may sell a lot of albums, even if no money was spent on very little money was spent on advertising the new album, right? If artists are less popular, that might not be true, right? So they might need this extra money. So there might be some interaction, right? Also between these additional predictors and so the money that is spent on advertising. So and that is possible. A second thing so that you have to keep in mind is that you might accomplish a better looking distribution if you transform so one of your variables. And here we already know that so sales advertisement budget is positively skewed, right? So and that's what a straightforward thing would be to see whether transforming so the advertisement variables or predictor so to whether that will reduce the positive skew and whether that will make our distribution look better, right? So and that's something that we'll try later. And then, of course, we always have to check whether that is actually problematic for the model estimation, so for our regression itself. All right, so before we talk about this option to transform the data, so let's take a look at the residuals plot again as a reminder. So here on the x-axis, these are the fitted values, so that are our y-heads. So that they basically what the regression function predicts for a particular case. And then on the y-axis, we have the residuals. And then, of course, we're sort of, if there's a positive relationship or a linear relationship between our predictors and the outcome. So what this plot does, it's just taking out this linear trend, whether it's positive or negative, right? So there's a line that's like this or like this. So it's taking out this trend because we're basically looking at the, right? So we're plotting these fitted values here on the x-axis. And so, and then, so our residuals should just spread around 0, right? So for each predicted value, so right in the original data set, so that, right? So basically that is our, so these are our predicted values, right? So we're basically taking the values here on this blue line, right? And we are now plotting them here on the x-axis. And then what we are plotting, basically so just if you want to think about this diagram, just think about it that way, right? So we are taking this data here, so this plot, and we're just rotating it, right? So here it's like this. So and then just take the blue line and rotate it to horizontal, and that's what more or less, right? So that's what you see here. Yeah. So you're just bringing that down, because you're interested in how basically what you're plotting here is nothing but how much do the values spread around these predicted values, right? So you're basically plotting the spread around the regression line. And because you don't want to look at this in an angle, it's much better to look at it as a horizontal line. That's what this plot does. And then so this dashed line here is just for you as a visual aid to see where your right, basically there's a mean of the residual should be. So that is 0. And then the red line is the actual mean. And here you can see that looks pretty good, right? So that looks pretty good. So there's not like a systematic trend or something like that. So they're all pretty much, so they're spreading relatively evenly around 0. And then the fact that you have like, so the data is concentrated here on the left side, it's just because they're skewed, right? So that's consistent with this idea that they're skewed. And so this here does not mean that necessarily the variance of the residuals is smaller, it's just you have fewer data points here, right? So if you have fewer data points, you wouldn't necessarily expect them to be here, right? So that would actually something that's rather inconsistent with the assumption that they have the same variance, right? Because they're supposed to be normally distributed. Now, if you draw only like one data point from a normal distribution, then your expected value is a mean. So, or 2, right? So there shouldn't be like here. All right. So it's different if you see this funnel shape, right? So that is not a good sign. And if you have like the same, especially if you have the same concentration of data in all across the entire spectrum of your fitted values. And then you see here, so what R does when you use a plot function. So the plot function, by the way, gives you 4 plots in total. If you want only one particular plot, you can use this which argument and so just use the indices, right? And then we'll plot only this particular plot for you. And so the residuals versus fitted plots always the first one. However, so what R does for all plots is so it gives you so the IDs or row numbers for cases that are a little bit unusual, right? So they deviate from the rest of the data, that are potential outliers or suspect cases. And it's nice because so that gives you like an indication what data points you may want to look at more closely. All right, so so we see here, right? It's for our data set, it's 142 and 169. All right, so as I said, so what we probably want to do is we want to see whether we can transform the data a little bit and to see whether that helps with our obviously as a distribution of the residuals, etc., etc. And so since they're moderately positively skewed, so let's try a square root transformation that we're doing here. And so that actually looks much better already, right? So we still see that's a little bit like looks a little bit like bimodal, but so as if you had like either you spend less money or spend a lot. So and then so as you can see here, right, if we do the scatter plot, it also looks much better than before, right? So in terms of so the spread of the data, and so and if we basically now if we check how the transformation actually affects our fitted model, then we see not much. So the so both our regression coefficients and so I mean, of course, it's numerically there's a big numerical difference because we're in a completely different scale now, right? So that is not surprising. So it's 4 as compared to 0.1, but so the t-value is actually very similar, and also our R squared is very similar. It's a little bit lower, but so it's more or less. So that means it was probably not a big deal, right? So this skew that we had, so that did not fundamentally change. So the model estimation, and so that is basically the same right plot for our transform data here. So again, looks pretty good. So right, nothing that we are worried about. And then it's also what we always want to do is to look at the so-called scale location plot, which is very similar to the residuals plot. It makes it a little bit easier for us to identify heteroscedasticity, right? So because rather than checking by eye, so whether in all, right, whether across the entire spectrum of fitted values, the spread is roughly the same. So any changes, right, in the variance of the residuals is here reflected in the slope of this line. That means if there's heteroscedasticity, then this line would be non-horizontal, right? So then we would have a trend in the line. So it would be like positive slope or negative slope. We don't see that here, so no concern. So it's all good. Yeah, and so then if you want to, you can also do a formal test of the heteroscedasticity. So there are different options and are available. This is just one option. And then, after I've told you how nothing is heteroscedastic here and everything looks good, the test is significant. But so keep in mind, always the same. So it's a large sample. So even small deviations probably give you a significant result here. So that wouldn't freak me out. Still not very worried about that. And in our case, so the heteroscedasticity is most likely caused by these 3 outlying values here that have particularly large residuals. And so if you want to check whether that's true, right? So we just run the diagnosis again. So after excluding those data, right? So we basically we remove these 3 cases from our data set. And so that improves actually the R squared quite a bit. Well, not quite a bit, a little bit, so it helps, it actually makes the model better. And so it's also, so the test for homoscedasticity, basically now we can keep the null hypothesis, right? So that the data is homoscedastic. So that's good. So these three cases were clearly the troublemakers here. Again, doesn't necessarily mean you have to exclude them, right? It's just, in this case, we don't know anything about the data, but they deserve further investigation. All right, so to check whether the data, whether the errors just are normally distributed, we can do the QQ plot, right? Which also in this case is not super concerning. We see a little bit deviation here in for the larger residuals. So that means the largest residuals here, again, our three suspects. So the largest residuals are a little bit more extreme than we would expect if the residuals would follow a normal distribution, but it's not super extreme. So that is right. It's not, you don't have like a 30 here or 10. It's a 3. So that is still not super concerning. Apart from that, looks almost perfect, so that looks pretty good. And if you exclude these the 3 cases here, then you see it's, I mean, it couldn't be any better. So that makes it perfectly normal. So no worries about the, so also here you see that even if we don't exclude the outliers, the Shapiro-Wilk test is not significant. So the errors are definitely normally distributed here for such a large sample. So that, I mean, absolutely no worries here. Okay, so, okay, let's try to spot the influential cases now. So a good thing is so that we normally want to start with. Sorry for plotting all of these here for some reason. So it would give me a funny. So Markdown will give me a funny plot if I try to index it. So that's why I had to include them all. But what I actually wanted to show you, we were talking about last week already, is this leverage versus standardized residuals plot that also has Cook's distance included. And then, so just as a reminder, so leverage are the extreme, cases that have extreme X values, so or unusual, let me say, because it's not necessarily extreme in terms of the absolute distance from the mean, but they have unusual X values. So the further away, so basically the more unusual, the more extreme and X values, or the big their value is for a case, so the more potential it has to influence the regression line. So the more, but only if it has a large residual, right? So if it's basically a case that is does not agree with the rest of the observations, so this with all other, so basically has an unusual location relative to the data cloud, then it pulls the regression line towards it, right? And that is only true for unusual X values, right? To remember these plots that we had in the lecture. And so that means you look for cases that are here in this corner or here in this corner. And so it also always shows you a Cook's distance, but that is a relatively liberal criterion here in this plot. So and you can see it's not even in the graph, so that is really nothing to be worried about. But so we'll see later that you could actually apply a more conservative criterion, and then you could identify more cases as potentially influential. And then also just a reminder, because that is super confusing, we talked about that last week, but I want to explain it again. So other measures that are important to determine whether a case is influential or not are your standardized residuals, the studentized residuals, the leverage, and then of course the Cook's distances. And then again, it's super confusing because different textbooks use these labels. This is slightly different, so they sometimes mean different things. So when we are talking about standardized residuals, then in most cases, I would say 95% of the cases, so what the textbook or the source means are what is also called internally studentized residuals. Yeah? So it's basically the underlying idea is to make the residuals unitless, yeah, by dividing them by their standard error. That's similar to the idea of a Z transformation, right? And so that way we are creating these standardized residuals. This is a formula. So you can see, so it depends on this RSE is the residual standard error of the model. So that's basically our estimate of our residual standard deviation, right? So that we estimate from the model. And it also depends on H, so this HII here is a leverage for the corresponding observation. So it also depends on the leverage. Long story, it's actually a bit more complicated. So why you calculate the so the standard errors in this way, it has something to do with the fact that actually due to the fact that, so due to the way how we estimate the regression model, so that the errors of the residuals have to sum to zero, they're actually not independent, right? So but that is only for due to the way we estimated them, and that's why it's a little bit more complicated to actually estimate the standard error. Not important to understand it in detail. Just wanted to mention it here. Important is that the standardized residuals follow a t-distribution, and that means so we can, in order to determine whether so some residual is extreme or yeah, somehow is unusual, so we can compare to what we expect under a t-distribution, right? And if that means if it's like more than 3 standard deviations below or above the mean, which in this case is 0, right? So we probably want to flag that observation and scrutinize it a little bit more, right? So because this can be considered an unusually large residual. Okay, right? Because only 0.2 roughly of all observations should have a residual that large. So if you have a lot in our data set, so it might be worthwhile looking at them. And if you do that for our data set, right, so we are using the R function, R standard, right? So that gives us an internally studentized residual. Again, internally studentized is, so that means we are using this particular, so that when we are estimating, so the standard error, so then we are including this particular value in our estimate of the residual variability, right? So that means if we calculate the mean residual, so the mean residual sum of the mean squares for the residuals, we include this observation in this estimate. Okay, yeah, and we're using our standard to do that, and then you could either flag anything that is has an absolute value larger than 2, right? And then you can look at the data points. So this is just the corresponding advertisement and sales numbers. And then if you want to know what case it is, then we see, right, it's 1 that we had already flagged earlier, 10, 42, 50, right? So we see the 42 again, we see the 169 again. So that's basically confirmation what we saw before. A few more, but then again, so large residuals alone are not necessarily a problem. They also have to have large leverage, right? So they have to really influence the regression function. So and if we do that with the 3 standard deviations, so so larger than 3, then we see it's basically only 1 left. It's the 169. And so studentized residuals are the ones that are very similar to the standardized residuals, just that they kick out so this one data point that we are calculating the residual or the studentized residual for. They kick it out when they estimate the mean residual. So the means. It's so hard for me to pronounce this. So the mean sum of squares for this for the residuals in the model, right? So then this data point is not included in this estimate because it, right? So the underlying rationale is because it could be so influential, and it could basically bias the location of the regression line. So that's why we want to take into account that if we do not use that data point in the estimation, so how far away from the regression line would that case be, right? So because there's always this possibility that this point pulls the regression line towards it, what makes the residual smaller, right? So we want to know if we basically don't include it, what would it look like? Okay, so that needs to be taken into account, right? So that is, we are using the function RStudent to calculate these. So they're also called like externally studentized residuals, deleted residuals, or jackknife residuals, right? So these are different terms that are, and we see, right, it's also only 169 here. And case one, sorry. So 1 and 169 here that have large, so that basically have large studentized residuals. All right. So then if you want to look at the leverage, so again, leverage, as that is basically leverage tells you what is the potential of this case to influence a regression, right? It doesn't necessarily, if it's in an alignment with the pattern that we see in, so that we're estimating from all other data points, then it does not necessarily mean it's biases our results, right? So if it's basically, right? So if it's close to the regression line that we estimate from all other data points, and there's no worry, there are no worries. But so if that case would have a large residual, so then it would influence the regression line a lot. So, okay. And that's why it's called like leverage. So leverage is always a potential for bias. Right? Does not necessarily have, it has to go along with large residual, right? So leverage is a potential for bias. So in order to determine also leverage, we use the function head values. And so that will give us the leverage for each data point in our sample. And so we wanna, so like a rule of the thumb is that so it shouldn't be more than 3 times the mean leverage value. The mean leverage value can be calculated as, right, so the number of predictors plus 1 divided by n, so by our sample size. So in our case, we have 1 predictor, 200 data points, so that means our head values shouldn't be larger than 3 over 100. So our leverages here, and if we check where this is violated, then we see it's 11, 23, 43, 87, 88, 184. And so most importantly, those do not overlap with the cases that we have identified as the ones that have a large studentized residual. That's good, right? That means they are potentially influential, but they actually correspond well with the general model. So that means we don't need to be too concerned. We have to take that with a grain of salt. So keep in mind what we were talking about last week. So that if you have multiple outliers, or this whole system starts crumbling. So that is basically only for identifying one outlier. We will talk about that next week. So what might be alternative approaches to make sure that the regression is not biased by outliers if you have multiple of them, so multiple outliers, right? Okay. So, okay. And then also, right, so the last thing you could do is to calculate Cook's distance. And Cook's distance is a measure that takes into account both, right? So the leverage, so the potential, and the residual, so the discrepancy, so how unusual basically the y value is, so how much it deviates from the regression model. So that is fitted based on all other cases, but not this one. So, and that's what we're actually interested in. And then there's also rule of thumb. So the Cook's value shouldn't be larger than 4 times the mean. And that is a more conservative, so that's a more conservative criterion than what we used, what the plot here is using. So that's very liberal here, right? So this, what you see for Cook's distance. And so here, that is a more conservative criterion. And if you use that, so right, again, R has a function Cook's distance. So you just basically call Cook's distance, and then you give so your estimated model as the argument. You do that for all of these functions, right? So just gives a model, so the estimated model as the argument here, and it will calculate all the distances for your entire data set, and then you just pull those out that are larger than your threshold. And in this case, right, so it identifies the 1, the 3, the 10, the 42, 55, 125, 148, 169. So we already know 93 here, we're a little bit suspicious. It gives us a few more, so it might be worthwhile checking those as well. And then finally, so last thing, so R has also something that is useful, which basically that is a actually a package that has all these, the Cook's distance and the R student, R standard are all functions within this like bigger package or component. So, so you can also use a function that's called influence.measures. Again, so you give it so your estimated model as argument, and then it gives you most of these and more. So indicators or statistics that we have calculated above here for your entire data set, right? So you see that. So here you have the DF betas. So we will, and the DF fit, we will talk about that next week when we're talking about multiple regressions or Cook's distance, your leverage values. And then based on so the combined consideration of all these criteria, it highlights for you potentially influential cases with a star. So that means, right, so here you you go in and you see, and that is actually more conservative than anything else that we were doing before, right? So, and you, if you want to do that, right, so you could just inspect those cases that are highlighted here a little bit more closely when you're doing your own regression. And that is really so probably most conservative. So it's not necessarily the case that all these data points are problematic, right? So that might just give you an indication which data points you want to check more closely. And then, so when I say checking more closely, that always requires knowledge of the data set, right? So you have to, it has to be your data. You have to know how it was collected. You have to know whether there's, and when I say check these data points, and it means make sure there is no data entry error, make sure that there is no, there was no malfunction of the equipment. So make sure maybe if it's like, for example, human participants, and you have, so ideally testing protocols, you can check the notes. So was there something unusual with this participant? So did they ask a lot? Did they seem tired, right? So was there, if you do animal studies, was like, I don't know, on this day was the AC was not working properly, was super hot, or was I don't know, the mouse seemed sick. I don't know what could be the case, right? So, but it's very important so that you have additional information, that you, more importantly, that you know how the data were collected, that you know the order the data were collected, who collected the data, so whether they were they're from different, right, collection phases, et cetera, et cetera. So everything that helped to determine whether anything could be wrong with a particular data point, right? So, but that is nothing that you can determine just based on the data alone. All right. Okay, so the last thing I wanted to talk about today, and we will actually not talk about it that much in class because we have talked about it already, so it's more about the implementation. The idea is always the same, is about bootstrapping simple linear regression. You can do that for multiple regression as well, so same principle applies. And so the situations in which you want to consider bootstrapping is when your assumptions are violated. Not if you have a lot of influential cases. So bootstrapping does not necessarily help with the influential cases. So then you should rather use robust regression, which we will talk about tomorrow, which also combines bootstrapping with. So, but that is an unrelated issue. So, so with certain, so basically certain methods to basically down value or down weight the so the cases are considered influential. So bootstrapping is if you have problems with non-normal residuals, if you have problems with so heteroscedasticity that you cannot get rid of. Yeah, so if we have problems with maybe the linearity assumption that you cannot correct by changing your model, for example. So then you want to consider bootstrapping. All right. So because then the sort of assumptions for the inferential tests to test the significance of your regression coefficients and of your R squared, so these assumptions are violated. And you have to estimate your own sampling distribution. It's always the same idea, right? So if you want to bootstrap a regression, so you can use a boot function that comes with the boot R package, right? And so as we did last time when we were estimating the confidence intervals, so you have to write your own function. So you have to define the function that tells R or that tells boot what actually, how you want to calculate the statistic for each so bootstrapping sample, right? So for bootstrapping, right, just a reminder, you basically you take your sample and then you basically keep drawing. So samples, basically you treat your sample as a mini population. You say, okay, I assume this is a representative sample for my bigger population. Right, so and now I treat that as my mini population. I will just sample, repeatedly sample from this mini population, and then I will estimate. So that way I will approximate or estimate the sampling distribution, which I cannot define otherwise because the assumptions for so for how the sampling distribution should look like are violated, right? So that's why I have to come up with my own estimate. And so it's sampling with, so for bootstrapping is always sampling with replacement. So that means, and basically the sample size for each iteration of the bootstrap is normally the same as your entire sample, right? So that means you have 200 in each bootstrap sample. But it could be, for example, you could select, because it's with replacement, you could, for example, sample the first album 5 times or 20 times. Right? So that's why each bootstrap sample is different. Okay. So, and then basically you draw, in this case, right, we are drawing 10,000 samples, and then for each sample, we fit the regression model, we estimate our parameters, and that way we create our own sampling distributions for our intercept, so for the coefficients, right, for the intercept, for the slope parameter, and also for our R squared. So we're basically just doing it by hand. And that's why I like the bootstrapping, because, and that's why I'm reminding you so often of it, because it also reminds you how it actually works, right? So what the regular tests are doing. Just in this case, you derive, and normally the sampling distribution is a theoretical construction. You derive it based on theoretical assumptions, and here basically it's more an empirical thing, right? So you're actually doing it, and then you're approximating your sampling distributions. All right. So, and you, as I said, so you have to write your own function. That's the only really difficult, but the only thing that's a little bit more difficult about it than running your regular test. So you have to tell R, so on each iteration of the bootstrap for each sample, so how to calculate the statistics. So how to calculate the regression coefficients, how to calculate R, and you actually don't have to do it by hand. You can use the functions, the functionality that's already implemented in R. You can use LM. So, right, it's not hard. It's just boot is simply a function that you can use for everything, and that's why you always have to tell it what it needs to do. So, and here, right, so we tell it, so we first define the number of iterations, and then we are defining, so the function that tells, later tells boot, so what it's actually supposed to do with each of these samples, random samples that it draws from our 200 album sample. And so, right, and that's just a definition. So this word here just tells us now we are defining, tells R now we're defining a function. These are the arguments of this function, so we call them formula, data, and indices. And then after these curly brackets, we tell the function what's actually supposed to do with these arguments, right? And then after return, we are telling the function what it's supposed to output. So, so whenever we call it, right? So basically, right? So we input something, then the function does some transformations here, and then it outputs something that we can work with later on, or that R can work with. So right in here, we just have to input a formula. That's the same formula that, so that's basically just a formula that LM needs, right? When we call it later, then the data, that's also, right? It's just the data from the data frame. It's just the particular data set that is required. And the indices is just your basically your particular, so your iteration I, basically. So that's the specific iteration that R is currently working on. All right. So that allows boot to select a sample, right? So this is basically just to define sample, which is called D here, right? And so this is just fitting your model, right? And you do that in the same way that you would use your LM function if you would fit a normal model, right? So just in this case, it pulls a formula from the argument that you give so this function here. And of course, the data it takes from here. And so, and then it returns your coefficients from this model, right? So basically, so coef just extracts the, so the two regression coefficients, so in this case, intercept and the slope, from your fitted model. So, and then after you define this function here, you can actually call boot, right? So we call that boot results. And then you just say, okay, the statistics that I want to calculate, which in this case are like, right, so multiple, so it's like actually fitting your regression model. So please calculate, so what you're supposed to do with each sample. So please just call boot rec, so that is defined here. So do what I told you to do here. And then, so you give it the formula, right? You basically just list the arguments that you specified for boot rec above, right? So you give it so the formula. So sales is predicted from AdWords. The data are album simple, and then as a number of iterations. So our indices are just the 10,000, right? And so. And then R starts doing that, right? So, and you can look at the results, right? So if it's done, so, and it tells us here, right? So that is the first estimated parameter is our intercept. And the second estimated parameter is our slope. So it's a bias, so it's very, it's not that small for the intercept, but I mean, it's also not big, right? The intercept is relatively large, so it has a very small bias. So that means this corresponds very well to the mean of the sampling distribution. And so this is the corresponding standard error, right? So the standard deviation of the approximated sampling distribution. You can pull out the confidence intervals from your results, right? So in this case, the 95% confidence interval for the intercept is 119 to 150. And so for the slope, it's 0.08 to 0.11. And so you can also plot the sampling distribution for your intercept and for your slope, right? That's for the intercept. You see, it looks all very good, right? You see, so that's of course the mean is the so what boot gives you as the parameter estimate. It looks very well behaved here, and so it's nice and symmetric, so really great. So, and that is for the slope, right? And then you can do the same thing for R squared. The only thing here that changes is that, so this time you want the R squared value, right? So not the coefficients, and then you can do the same thing, right? So you get 0.33, so that's basically identical to what we got before, and then it also looks fantastic. So on the 95% confidence interval between 0.22 and 0.44, more or less. Right. So that's how we do the bootstrap for regression. So it's pretty simple and straightforward. All right. So then I would say for the remainder of the time, you can either discuss. So I mean, let me actually create the groups again. And then you can just hang out as long as you would like. You can also leave if you have nothing to discuss. You can start at least if you're done with the assignment that's due tomorrow already, you can maybe start reading or discussing the next assignment a little bit, despite the fact that maybe you don't have all the information yet that you need for it. So whether everything is clear in terms of the questions themselves, and whether the wording is clear, etc., etc. And if you want to talk to me during my office hour, just send me an email. So I'll be around. Let me know whether you have any additional questions. Yeah. Do we want to do that? That I can create the 4 groups again. So, and then you can just touch base with your other. Yeah. No.
Okay.
All right. Yeah. Okay. Did that was that helpful, or was it too redundant? So did that help today to go over?
I think it puts some things into perspective, for me, confirm some things that I had been thinking about, but maybe would have been a little bit unsure of.
Okay. Alrighty. Yeah, I mean, it was a little bit redundant, but I think, I hope it helps to hear things multiple times and makes them stick. So I also, I will actually update the slides on Blackboard. I will include a few more plots that show like residual plots that show problems like heteroscedasticity, non-normal or non-linearity in the residuals, etc. So I will give you like a little bit more examples of what it should look like. All right, so perfect. Then let me stop sharing, and then I create the breakout rooms. I will just create 4, right? And you can just join them, and then just let me know if you have any questions, right? So I will leave that session here open until 7.
I had a question about one part A. For part A, when you say the regression coefficient for SES is significantly different from 0, it was clear, like for that one, I knew to look at PR is greater than the absolute value of T. Yeah. But then when you said, is the regression model significantly different from a null model? I wasn't sure whether you were saying the same thing or whether in this case the F-test would be the appropriate statistic.
Yeah, it's the same. So they are equivalent. So for a simple linear regression, so whether you test your, so the slope, so that whether you look at the t-test for your slope parameter, or whether you look at the f-test, it's the same. So they are interchangeable. So they're the same thing.
Okay.
So you can even mathematically transform one into the other. You can show that they're equivalent.
Okay.
So that means both would be okay, right? So you can, I would prefer if you would look at the F statistic and test the R squared, because I'm asking you whether the model is significantly different from the null model. And for any other case, so if it's not it's a simple linear regression, if you have more than one predictor, then you would have a problem if you just look at the individual t-tests. So that's why it's I think it would be better to do it anyway, so to look at the F statistic. But in this case, you can also look at the T value.
Okay.
Dr. Unger, I think I was assigned to the wrong breakout room. I think I should be in 2, but I was assigned to 3.
Yeah, me too. I was assigned to 1.
I did not assign anyone. Wait a second. That's weird. I will reopen them. Maybe I just created 4 groups. I did not do any assignment. Okay, 1 second. So it takes 6 seconds to close the rooms, and then I will redefine.
Okay.